Hey, and welcome. In this video, we're going to be looking at 10.6, which is the volume of prisms and cylinders. So to start us off, let's just take a look at what volume is. And volume is the three-dimensional space that an object occupies. So what we're going to be looking at here is in 3 dimensions, how much space that it is filling up. So we're using 3-dimensional units like cubic meters or cubic feet, etc. And what that just means is that if I have a 1 foot by 1 foot by 1 foot little cube, how many of those little cubes fit inside of our 3-dimensional object? Okay, so today we're going to be focusing on prisms and cylinders. We'll look at some other objects later. But in order to find the volume of a prism or a cylinder, the thing that makes something a prism or cylinder is that they have those congruent parallel faces. And since we have those congruent parallel faces, those bases, we are just stacking those bases up a certain height. So the volume of a prism or cylinder is big B times H. So this big B base is the area of your base. Think about if you stack up a bunch of papers that are shaped like your base, H high, that will give you your volume. So we need to find the area of that base, which means we are going to need to know all of these previous formulas that we have been using in order to find areas like parallelograms, triangles, circles, regular polygons, anything else that we might need to find the area of. So let's jump right into some examples here and take a look at some 3-dimensional shapes. So this first one, we're looking at finding the volume of this right rectangular prism. And you might have thought of length times width times height before for a rectangular prism, which does work. The reason that we want to use that big B times H, the area of the base, times height, is because it works for rectangular prisms, but it also works for triangular prisms or cylinders or pentagonal prisms or any sort of prism or cylinder. So it gives us a lot more flexibility to use it with whatever shape we're looking at. So since we have a rectangular prism here, it really doesn't matter which rectangle is our base, since they're all parallel congruent faces. So we're going to look at, for this example, this piece right here as the base. So to find the area of the base, big B, we're looking at just base times height of this rectangle here. So that's just x times x minus 1. So we get a little algebra practice with this example as well. So our big B, if we simplify that, is x squared minus x. Okay, so if we're finding the volume of this prism, we're going to do that big B times its height. Well, the height of this, as we can see, this is a right relationship there. So the height of this prism is x plus 2. So if we are going to find the volume, our volume is going to be that big B, x squared minus x, times the height, x minus 2. So again, just practicing our algebra here, we're using our geometry equations to do that. So if we are multiplying a binomial times a binomial, we are going to distribute everything to everything. So x squared times x, here I have 2 factors of x times another factor of x. That's x cubed. X squared times negative 2 is negative 2x squared. Negative x times x is negative x squared. Negative x times negative 2 is positive 2x. And then we just check to see, do we have any like terms we can combine? And these two do combine. So we have negative 2 of them. We're subtracting 1 more, negative 3x squared plus 2x. And so this is our volume here, this guy. And we want to make sure that we still include our units. So if this is centimeters, 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 we're taking centimeters times centimeters times centimeters. So just like x times x times x, that's centimeters cubed. Okay, let's take a look at another example with a little bit more complicated shape. So we're finding the volume of this pentagonal prism. So we have to remember, how do we find the area of a pentagon? Because big B is a pentagon. So when we're looking at that pentagon, we're using the triangles within the pentagon. So we can use this guy here and then say there are 5 of that triangle. So they already gave us the side length here of the pentagon. We're going to assume this is a regular pentagon. We probably should have been told that. And that this apothem here is what we need in order to find the area of that triangle. So the nice thing is they did a little work for us. They found that angle here, which is your central angle divided by 2. So we're just going to use half of this 5, which is 2.5. And this 36-degree angle to find our apothem there, which is the height of that triangle. So we're looking at opposite adjacent, so that's tangent of 36 is equal to 2.5 over A, opposite over adjacent, which means that A tangent of 36 equals 2.5. So A equals 2.5 divided by the tangent of 36. Okay, so if I want to find the area of this triangle right here, it's 1/2 of your base times your height. So 1/2, our base is 5, our height, you could type this into your calculator, right? That's just a number. Remember, we want to avoid any rounding error. So if you do type it in your calculator, make sure you use this exact answer that you get here, which is about 3.4409. Or you can actually just put in that into your equation here, however you want to do it. So 1/2 base times height, that's the area of this triangle, and it's pentagon, so there are 5 of them. So let's find what that actually is. 1/2 times 5 times 2.5 divided by tangent of 36 times 5. So the area of that pentagon, our big B, base area, is 43.01. And again, that's a rounded answer, so let's use the exact thing when we're finding our volume. So this is big B, so in order to find the volume, we just have that big B times the height of my prism. And I know it's very tempting to want to say, or height is somewhere here of this prism. Height is always the distance between your two congruent parallel faces. So in this case, the distance between these two pentagons is 7 meters. So we're just going to take that exact answer here in our calculator and multiply it by 7 to get our volume, which is about 301.08. And our units are meters, and we did meters times meters times meters, so meters cubed. Okay, a couple more examples here. Let's flip over to look at finding the volume of a cylinder. And the nice thing about volume, we talked a little bit about right and skew three-dimensional shapes with our surface area and how that can affect your surface area. The nice thing about volume is that it does not matter if you have a right or oblique cylinder. Think about if you have a stack of discs and you just kind of nudge them over the sides so that they're not a straight stack of discs, you still have the same amount of disc. It's just no longer in a straight straight up and down stack. So we can still do the same thing to find our volume. Our big B, the area of base, in this case it's a circle, so pi times your radius squared. Okay, and then to find our volume, we're going to take that pi times the radius squared times the height, which needs to be that perpendicular distance. So if they gave us this here, maybe that's, I don't know, 14 or something. Want to make sure that you're not using a slant height to find volume, rather you're using the height to height. Okay, from there, we're just actually going to do that. So if you want it in terms of pi, you just do 12 times 8 squared. It's 768 pi cubic centimeters, which is about, just multiply that answer by pi to get about 2,412.74 cubic centimeters. Okay, well, last but not least, we're going to talk about some dimension changes. So this is something we circled back to with area as well. But when we're changing our dimensions in a shape, how that affects your volume is going to be dependent on the fact that it is a volume. So if we're changing the dimensions, so in this case, all of them, the radius and the height by 1/2, think that whatever I'm doing with this, right, we have pi times your radius squared times your height. So you have pi times your radius times your radius times your height. If we change each of these by some factor, you're changing your volume by that factor 1, 2, 3 times because of that three-dimensional shape. So if you're changing your height and radius, all of your dimensions of your shape by a half, I don't even have to figure out the old volume and the new volume. My new volume is going to be changed by that cubed because it's a volume. So this would be 1/2 times 1/2 times 1/2, which is 1/8 times the original volume. Okay, and this would work for any change in dimensions. As long as you're changing all of your dimensions, you're keeping it a scale of your original figure. So if you were tripling your original dimensions, your volume would change by 3 cubed, which is 27 times larger. If you were doubling the dimensions, your volume would change by 2 cubed or 8. So this cube, because we're multiplying by those 3 dimensions, no matter what volume you're finding. So that is all for this video. Thank you so much for watching.